talk about atoms in optical tweezers. I'd like to introduce Sylvain Schwartz from our own Harvard lab. Sylvain will be talking about the 1D atom array experiment.
Hi everyone, thanks for the introduction. So I'm very pleased to be here to talk to you about our recent results on this Rydberg atom array experiment. And by recent here I mean that most of the data I'm going to show you today are less than a month old, so we have still open questions, and we are looking very much forward to your feedback and hopefully follow the discussion after the talk. So this experiment is performed here at Harvard in the group of Misha Lukin in collaboration with Manuel Andres, Vladan Vuletic, and Marcus Greiner. And so, as most people in the room, I guess, our motivation here is to investigate neutral atoms as an elementary building block to make quantum machines. And we're especially motivated by that because of long coherence time, because of the nice AMO toolbox, which makes it relatively easy to prepare large ensembles of neutral atoms, and also by the fact that they're indistinguishable, which is a strong asset for such an elementary building block. But of course, there are also challenges to address along this way, among which are how to individually control these neutral atoms in large systems. For example, how do you make a zero entropy state to start with? And of course, how do you make these atoms interact over reasonably large distances? And so our approach to these two challenges is to make large arrays of neutral atoms with single atom positioning and imaging, and to make these atoms interact along the array by coupling them to a Rydberg. And so I hope after this talk you'll be convinced, if you're not yet, that by mixing these two ingredients, what we get is a versatile and promising platform for quantum information and many value physics. So here is the outline of my talk. So I will first quickly describe how we actually make these strongly interacting atom arrays. Before moving to the kind of preparation of some particular many-body states, known as Rydberg crystals, where basically Rydberg excitations are evenly spaced across the array. Then I will say a few words about how we are starting to probe quantum phase transitions into these ordered states. And finally, I will share with you some intriguing data that we have recently observed about the dynamics of these many-body Rydberg crystals after a quench. So let's start with the atom array. So the philosophy here is to use a bottom-up approach, as proposed in this picture, to the top-down approach that would be, for example, optical analysis. So for this bottom-up approach, we start with a high number of tightly focused optical tweezers, say typically 100 in our case, which are in this collisional blockade regime where they can be loaded at most by one atom. And then the idea is to get an image of the atomic distribution across this array of traps, and to use this information to turn off the empty traps and rearrange the other into the desired pattern before switching on Rydberg interactions. So at the heart of our experimental setup is this acoustoptic deflector, in which we send like typically 100 RF tones, which result in 100 diffracted beams, which are then focused through a high NA objective into a vacuum chamber, resulting in 100 traps. And then a typical experimental sequence is to make a mod, wait for some loading time, then send some cooling and imaging beams, collect the fluorescence from the atoms through the same high NA objective which was used to make the traps, and make an image on an EM-CCD, and then use this image to apply some feedback on the echo. And so starting from an array of 100 traps, we typically get more than 50 atoms randomly loaded, which can then be rearranged, for example, into a defect-free array of up to, I think this one is 63 atoms, or other patterns like clusters of 2, clusters of 10, or basically any arbitrary pattern. One kind of only constraint we have here is the minimum spacing between the atoms, which cannot be made much smaller than 3 microns. And so to make atoms interact, neutral atoms interact at such distances, well, what we do is to turn on Rydberg interactions. And well, basically it turns out that the van der Waals interactions are nicely suited to our experiment, because for very reasonable values of the principal quantum number, say n equals 70, the van der Waals interactions are still the dominant term up to like 10 microns, which is 3 to 4 lattice size in our case. So we also like the fact that they are quite tunable, especially through the distance here, over which we have a good control in our experiment. And so what we get at the end of the day is this frozen Rydberg gas Hamiltonian, over which we have yeah, kind of pretty good control over all the terms. All right, so in practice, we initially prepare our rubidium-87 atoms into the f equals 2 and f equals minus 2 level of the ground state manifold, and then we use a stretch transition to Rydberg using 6p3½ as the intermediate. And now if the detuning from 6p3½ is large enough, this can be approximated by an effective 2-photon transition, which I will assume in the rest of the stuff. So I now have 2 parameters, which are this omega and capital delta. So experimentally, this is what it looks like. So we send our 2 Rydberg lasers along the axis of the array. So we kind of make some collective excitation to Rydberg, and given the laser powers that we have and the other parameters that we're using, we typically get a few megahertz of effective radio frequency. So now here's a quick recap of our kind of experimental sequence before I show you the data. So we take in total 3 images. The first one is to kind of sample this random distribution across the array of traps before performing some rearrangements. And the second image is here to check that the rearrangement procedure went well, that we kind of get this defect-free array to start with. And then the experiment per se, which is turning off the traps for a quick amount of time, typically a few microseconds, apply our Rydberg pulses, and then take a third image, which is kind of the result of our experimental cycle. And a kind of nice feature with these Rydberg atoms is that you get a detection mechanism for free, because they do not feel the trapping potential from the optical tweezers. So they just kind of fly away from the trapping region before you take this third image, and so they can just be detected as losses or empty sites. All right, so let's look at the data. So the first thing you kind of want to do with this Rydberg atom array is to look at non-interacting atoms. So you can just set the distance to be sufficiently large such that they do not interact. And what we see are nice Rabi oscillations. This is, for example, between Rabi oscillations between ground state and 71s state. And here, basically, the contrast is limited by our detection infidelity. I will not comment on the decay of other parameter, because I guess Harry is going to talk more about this to detail tomorrow at the interference session. So now let's kind of move on to more than one interacting atoms. And as long as you have more than one, you enter this physics of Rydberg blockade. And as you all know, as dynamics, for example, with 2 blockaded atoms occurs between this ground state and this symmetric superposition here with a √2 enhancement of the radio frequency, and this generalizes to the case of n atoms as long as they all sit within the same, within one blockade radius of each other. We still have this simple 2-level dynamics with a √n enhancement. And so, well, as a sanity check, we're happy to observe this on our experiment. So if you now make clusters of 2 atoms within one blockade radius of each other, indeed, what we see is this √2 enhanced oscillations as compared to the non-interacting case. We also see a reduction of the contrast by a factor of 2, because now we have 2 atoms showing at most 1 Rydberg excitation. Okay, so now we can scale up the cluster size. This is, and still do the same simple experiment. So this is what we get for 3 atoms, 4 atoms, 5 atoms, and as we increase the system size, it gets more and more difficult to fit an exponentially decaying sine function to this data. And if you still do it, this is what you get. So actually, up to a distance which is equal to the blockade radius, the experimental frequencies nicely fit to what you would expect. So this red line here is just the non-interacting frequency multiplied by the square root of n. And as you make your cluster size bigger than the blockade radius, then what this two-level simple description doesn't apply anymore, and you get more complex dynamics, which explains this deviation here. And while for fun we can keep scaling up the system size, for example, to 15, and now it looks kind of boring. It seems nothing happened when we try to drive Rabi oscillations on these kind of big clusters. This is because now we are averaging over all like atomic positions over one cluster, and now a different way to look at the data is to look at the probability of going to Rydberg as a function of the position of the atom within the cluster. And this is now a time kind of movie where you look at this. So as I start driving, initially the probability of going to Rydberg is kind of evenly spread across the array. But then, as I kind of keep driving, you see that some peaks of higher probability of going to Rydberg occur at the edges of the 15-atom cluster. And as I keep driving, I see now 4 peaks. If I keep driving to another time, I'm now in a position where I kind of see 3 evenly spaced peaks. So what you already see from this very simple experiment that there seems to be some interesting many-body physics occurring in this system. And now the question, especially in the form of this spatially ordered probability of going to Rydberg, and now the question is, can you do something cleaner to prepare such states where the Rydberg excitations would be nicely ordered across the array? And the answer is yes, we can, which will be the second part of my talk. So it's known from this 2010 proposal by Thomas Paul, Eugene Demmer, and Misha, that indeed you can prepare these Rydberg crystals by doing adiabatic sweeps across the transition. So to understand this, let us rewrite our Hamiltonian here and consider for a short moment that I switch off the interaction term, or I make it sufficiently small that it can be neglected. And let's look now at the last 2 terms that we have. So the first term, the tuning term, is kind of a chemical potential, which tells me the price I have to pay to add another Rydberg excitation into my system. And the interaction term here is kind of an offset price, which will depend on how these excitations are arranged across the array. All right, so let's look at what it looks like for the simplest interesting case, which is clusters of 3 atoms. And now I'm putting the energy dependence of the function of this detuning. So if I put my 3 atoms in ground state, I get a flat line at 0, of course. If I now put one more Rydberg excitation, I get this minus delta slope, which crosses the other level at 0. And now if I try to put 2 Rydberg excitations next to each other, I have to pay a huge offset price here, which is this capital V, which is my nearest neighbor interaction. And you should think at this capital V as being something extremely large, like much larger than any other energy scale in our system, so it is a huge price to pay. But now I can do something with, I can reduce this offset easily by just putting my 2 Rydberg excitations one lattice side apart. And if you think of it, when I do this, I just double the distance between the Rydberg excitations, which means I reduce this capital V by a factor of 2 to the 6, which is 64. And so now the offset is much smaller. Okay, and for completeness, I should add this other kind of possible state where all 3 atoms are in Rydberg, which has this huge offset, and also minus 3 delta. All right, so now that I have this levels, if I now turn back on the interactions, all my energy crossings become kind of anti-crossing, and in particular, the ground state like smoothly connects my initial state, which is all atoms in one state, to this spatially ordered state where every second lattice side gets excited into Rydberg. This is at least true for the case of an odd number of atoms. I'll come back to the case of even number of atoms later. So now, of course, the idea from this paper is to make an adiabatic sweep of the detuning. to convert this state into this one. So of course one could argue that if I go too far into my adiabatic sweep, at some point I hit the situation where this state with 3 Rydberg excitations, or all atoms being excited into Rydberg, becomes energetically favorable, and it is indeed true. So what we want to do is kind of stop our detuning sweep soon enough in the sweep such that we are not approaching this other kind of transition to all the atoms going into Rydberg. So as long as we do this, so as long as we sit somewhere far away from this region and also far away from the other one, which is 2 V's apart, then we can safely kind of say that our ground state at the end of the sweep is this spatially ordered. All right, so experimentally, this is what our numbers are. So this capital V is 24 megahertz. Then the next nearest neighbor interactions is this divided by 64, which is on the order of 400 kilohertz. And we typically sweep across the bare atom resonance from minus 10 megahertz to plus 10 megahertz. And our Rabi frequency is just basically a square pulse at 2 megahertz, which is a typical Rabi frequency. And when we do this for the 3-atom cluster, this is what we get experimentally. This is a Rydberg probability as a function of the atom position within the cluster. And you see that the edges goes to 1, while the middle one goes to 0, which also can be nicely visualized by these kind of histograms, which show the final state at the end of the sweep. And now, as before, I can scale up the cluster size, and this is what we can prepare in the 5 atoms case. This is for 7 atoms, 9 atoms, and 15 atoms, where we see that kind of some form of limitations start to show up in this histogram. All right, so far I have shown you data only for the even for the odd number of atoms. So, as I said, there's a reason why. The reason for that is that in the case of an odd number of atoms, you have a non-degenerate ground state, which is just this Rydberg crystal with 2 excitations pinned at the edges of the cluster. So the situation is a bit different with an even number of atoms in your cluster. So to understand this, let's look maybe at the simplest case again, which is a 6-atom cluster. So with 6 atoms, when I do this sweep, I can fit up to 3 Rydberg excitations into the cluster if I don't want to pay the price of this nearest neighbor interactions. So the first 2 will for sure be pinned where it's more energetically favorable, which is on the edges of the crystal. But then the third one, I'm not sure whether it should go here or here. Both configurations are energetically identical. And indeed, when we probe this experimentally, what you see now is the probability of occurrence of different many-body states, and you see that most of the time we prepare one of these 2 many-body states, which kind of some equal probability. Now, of course, one open question that we have is, are we making superpositions of these 2 crystal states by doing this? How could we prove this if we think it is the case? And how would this scale up with larger crystal sizes? All right, so now I'm going back on the track of making these crystals for an odd number of atoms by showing you the data for the 41-atom cluster. So this is the biggest cluster size I'm going to show you today. We're still working on making data for even bigger number of atoms. So what you see here is still this spatial ordering at the edges of the cluster, and it seems that not much is happening within this region in the bulk here. But actually, if you look at, for example, the correlation function for this data set, you see that things are happening in the middle, but actually it's kind of washed out because it happens for maybe different phases from shot to shot. By phase here, I mean just position into the cluster. But still from this correlation function, you see that we have some, at least, call it long-range order of maybe 4 to 5 lattice sites for sure. And then what sense to make of this data is still a little bit open to discussion. So now we can ask the question, what limits the crystal size to these values here, and also what sets the decay shape of these curves? These, again, are questions we're still working on. And yet another way to look at this data is now to look at single-shot images. So here, the first line that we see here is just a single-shot image of our initial state, which is just a cluster of 41 neutral atoms. And the other images are kind of, well, not so randomly selected images of what you get after frequency sweep. And so as a reminder, any empty site here should be a Rydberg atom. So as a guide to the eye, I'm just filling these empty sites with red dots, like that. And now maybe you kind of become visible on this picture that our typical state is made of kind of some chains with antiferromagnetic orders separated by defects or domain walls, which are highlighted with these gray rectangles here, whose number and position is kind of randomly distributed across the array. So of course we can now monitor the distribution of this domain walls. So you see that on average we get a few, maybe 6 to 7, and on some rare occasions here we get 0 domain walls, which means we are preparing the perfect Rydberg crystal with 41 atoms, and this is a single-shot image of this crystal here. Okay, so you could argue that this bar here is pretty tiny, so it's on the order of 0.6%, but actually we should keep in mind that our detection infidelities, even if they are quite small for one single atom, start kind of add up when we consider the many-body state with 41 atoms. And so if we correct for this detection infidelities, which we know, for example, from the single Rayleigh oscillation curve, then we estimate that we prepare this perfect crystal 8% of the time, even though we can detect it on 0.6%. All right, so this brings me to the third part of my talk, which is about probing quantum phase transition into these ordered states. And so our theoretical baseline for these phase transitions is this 2004 paper by the group of Subir Sagdev, who kind of studied the Hamiltonian, which is kind of an approximation of ours, where they assume an infinite nearest neighbor blockade, which then turns into this constraint that it's just forbidden to have two Rydberg excitations living next to each other. And they just consider only next nearest neighbor interactions here. And with this Hamiltonian, they kind of computed this phase diagram where you kind of change the next nearest neighbor interactions on the y-axis and the detuning on the x-axis. And so far what we have, the data that I have shown you occurs somewhere along this red line here. So to really probe this as a phase transition, what we want to have is some kind of order parameter, and it turns out that this number of domain walls that I just talked about is a kind of nice tool for this. So for the kind of ground state, or disordered state as we call it here, because of the quantum fluctuations induced by omega, the number of domain walls should be close to the system size, so the order of 40 in our case. And as you transition into this, in principle, perfectly ordered state, this should go to 0. So this is our experimental curve, and you see that it shows quite a nice, sharp transition between these two limits here, which is also enough now, although we're still working on it to claim that we think that the quantum phase transition here occurs at a point which is not the bare atom resonance, which was also predicted by Subir here in this phase diagram.
So it's a nuclear phase diagram?
It's
your 1D here.
Yeah. 1D starting from 6 times Newtonian.
No, it's not.
I don't think it's mean field. I think it's numerically. They somehow determine numerically this transition.
Yeah. Also, we kind of paste our.
I think they did determine. It's not just a sketch. I mean, this diagram is a sketch, but for some lines, I think determined.
Yeah, they determined it doing some finite size scale.
Finite size scale and numerically, exactly.
So there's a true phase transition 1D.
I think that's a claim from this paper. Okay, so another parameter we can look at, for example, also shows this nice sharp behavior is this correlation length fitted from this JT function that I mentioned before. And also exhibits sharp behavior at the same point. Okay, so now, as an illustration of the tunability of our system, I wanted to show you that we can explore different lines along this phase diagram. So for example, we can go into the Z3 order by increasing the next nearest neighbor interactions, which in practice, for our case, means bringing the atoms a little bit closer together. And as now we do this and make a sweep across this, along this line, we can prepare our system now to this three-ordered crystal where we get one Rydberg excitation every third lattice. And you see here how this builds up as we sweep into the first one. This is not the tuning here, but more the time into the sweep. All right, so now we can go even higher in V and go into this Z4 order. So here the model from this theoretical paper by Sagdev doesn't apply anymore because they were only considering the next nearest neighbor interactions. But we have kind of made our own sketched phase diagram to account for a longer range interactions, basically. And now, as you keep increasing these interactions, the interaction strength, we can now sweep into this Z4 order state, which is what you see here. All right. So in the last part of my talk, I wanted to say a few words about now the dynamics of this Rydberg crystal after a quench. So what we have been doing so far are these adiabatic sweeps to prepare this kind of nicely ordered crystal state. And now what we have investigated experimentally is, well, what happens if I now abruptly quench my tuning to be resonant again. So what if I'm driving now the Rydberg crystal and look at its evolution, and what you see here is some oscillations between actually two states. One is the initial Rydberg state, and the other is also a Rydberg crystal state, which is a kind of the complementary of the first one, where all the Rydberg atoms went to ground, and all the ground state atoms went to Rydberg here. And as I keep driving the crystal, well, it goes back to the initial state, and this goes on for a significant number of oscillations. So that was for a 5-atom cluster. Now we can scale up the system size, and well, an intriguing effect is that these oscillations seem to be pretty robust and independent of the system size. So this is, for example, what you see for 9 atoms case here. So these heat maps, so the left side of these heat maps are just the adiabatic sweeps to prepare the crystals, and then the right part of them are the quenches. This is the data for experimental data for 5, 6, 9, and 10 atoms. So again, for 9 atoms, you start from the initial Rydberg crystal, you go to the complementary crystal, and back to the initial one. And what's kind of intriguing here is that this feature seems to be pretty independent of the system size, at least in terms of frequency. And we can extract some numbers, and what we find is that the frequency of oscillation between the initial crystal and the time it takes to go back to this initial state is given by omega divided by root. Right? So, of course, we have made, so Hannes Fischler, more precisely, has made some simulations to confirm that indeed this is what we should expect. And what you see here are simulations for 17 atoms after a quench. So we start in the perfectly ordered crystal state. And you see that it's not kind of sinusoidal oscillation, but looks more like something which decays to 0. So here the population is kind of spread across the many different many-body states. And then at some point, the population of the complementary crystal emerges, then goes 1 to 0, and the other shows up, and so forth. And again, on this data, the frequency here is something on the order of omega divided by 2, and again, numerically, it's largely independent. So now we wanted to probe this. One of the questions is, does it still hold for very large cluster size? So the largest we have done so far is 41 atoms. So here we cannot directly look at the population of the many-body state because our signal-to-noise is not that good. A number of domain words which kind of show this form of oscillation. So here we have put on top the 41 atom experimental data with the 9 atom. So let me describe the 9 atom case. So here we start again from this nice perfectly ordered state where the density of domain word is low. Then it goes up into this disordered state and back down to a crystal state, which is a complementary one, then up again and down to the initial state. And so for 9 atoms, it's kind of well consistent with our data and simulations. And now we observe the same behavior of the number of domain words for the 41 atoms, which make us believe that probably the same many-body dynamics is happening for this 41 atoms cluster. And this has also been confirmed experimentally by simulations which came out yesterday evening from Hannes Fischer for 29 atoms. I think it's the highest they have made so far. And this again qualitatively agrees with our experimental data here, at least the frequency at which this oscillates. To contrast, we're still working on it. Apparently, it depends on whether we take into account the nearest neighbor interactions, for example, and also finite detection fidelity. So it's something we're still working on. Okay, so now, legitimate question is why do these oscillations occur at a frequency of omega divided by square root of 2, or at least something close to this value? And, well, we do have a very simple model to get this number, but it doesn't capture the full physics, but still, because it's simple and nice, I'm going to go through it now. So it's actually based on a dimer picture. So assume I have a dimer, so basically two atoms which are blockaded, and I start with having one Rydberg excitation on the right side of my dimer. So again, as a quick reminder, the whole dynamics occurs between the ground state and the symmetric superposition with a root 2 enhanced random frequency, and the anti-symmetric superposition is not coupled, doesn't see the field. And so having a Rydberg excitation to the right of this dimer means I'm now in the superposition of S and A. And what's happening if I do a 2 pi pulse at this root 2 omega frequency? Well, I'm going to get my symmetric state here will get a minus sign from these 2 pi pulse, and my anti-symmetric state will be unchanged. And I am now in this other superposition, which is having the Rydberg excitation on the left side of the dimer. So I need an extra 2 pi pulse to bring my Rydberg excitation back to its initial position. And because this dynamics occurs at square root of 2 times omega, and because I need two 2 pi pulses at the end of the day, the frequency of the full oscillation is given by square root omega divided by 2, which is this omega over square root of 2 that we are measuring experimentally. So now if I consider that my array, so my Rydberg crystal is just a collection of non-interacting dimers like that, then with this simple model, I hope you're convinced that I should expect this to oscillate between this and this at a frequency given by omega over root 2. But of course, this is not the full story. This picture completely neglects that these dimers are interacting, and of course they are. But, it also neglects the subtleties between the odd and even cluster size, like what should I do in the odd case of the last atoms to the right. And so one open question that we still have is why is this phenomenon so robust, and particularly so independent of the systems? And again, a few days ago, Hannes Fischer and Sylvain Schwartz came with kind of a simple yet accurate theoretical model which predicts actually more accurately the experimental measured frequency, which is actually closer to omega over 1.5. And so I encourage to talk to them if you're curious to know about the models they have. Sure. All right, so now as an outlook, I wanted to point out a few kind of things that are on our agenda. So obviously we could make some hardware improvement to go to 2D or even 3D, which is the new coolest stuff now, to study, for example, models. we could also implement individual atom control in the sense of addressing individually the atoms with our Rydberg lasers to go into the direction of quantum gates, and that could also be a nice tool to prepare some arbitrary kind of, well, at least some states, some interesting many-body states with this individual addressing. And we also have some ongoing discussion with Adam Harrow about how to kind of use this platform to maybe implement some quantum, one of their quantum approximate optimization algorithms. But okay, maybe more up the list in our agenda is keep on studying this space-time dynamics of Rydberg crystal. We're also very interested in probing these critical exponents at the phase transition, and especially we have now reasons to believe that our setup is would be a nice platform to try to observe this Kimball-Zurich type mechanism, where as you approach the phase transition, like your dynamics freezes at some point, and you get kind of a typical size for your, or typical density of domain world, say, which has a power law which depends on your critical exponents. So we kind of should be able to measure this and maybe tell something about the critical exponents of phase transition. And finally, another idea we're very excited about is investigating whether we could create entanglement in large systems by following this line of crystal superpositions. All right, so as a summary, this is a few highlights I have shown you today. So large Rydberg crystals exploring different ordered states by tuning the interaction, starting to probe quantum, or what we think is quantum phase transition, and observing the intriguing many-body oscillations phenomenon. So as a final word, I would like to advertise one spin-off of this project that we're making, which is to write people's names with atoms. And luckily, we have our first customer in the room, so it could be your name. Right. So with this, I wanted to thank like the experimental team who is working on day-to-day basis on this experiment, which implies also, for example, fixing the air conditioning. So Harry Levin, Alex Kisling, Hannes Bernin, and Ahmed Omham. Also to acknowledge theoretical support badly needed, so as I'm concerned, from Hannes Fischer and Suman Choi, and of course thank our PIs, Manuel Andres, Radan Bulitic, Marcus Greiner, and Michel. And thank you for your attention.
Thank you very much. We have many questions.
I would like to say about the crystal it is or not. Yeah? Usually we know about Born-Karman condition. Yeah? If you have a chain of atoms, yeah, you should have a periodical condition. Yeah? That means that topologically age of your chain are differing from atoms inside. Because of that, you have an even-odd alternation. Yeah? How to make the periodic condition a real crystal? My suggestion, maybe you may create additional interaction of boundary atoms. Yeah? Because if you have 17 atoms, each atom should interact and know about each other. In this case, I believe distribution and probability distribution of Rydberg state will be very different from what you have now, because you have a cluster.
It's very true that, especially in this, in any case, Rydberg excitations will be pinned at the edges of the cluster, and kind of the dynamics will develop from this kind of pinned boundary conditions.
Why you don't organize additional interaction between H atoms?
You mean by
this atoms, which may simulate,
We could do that, but for example, if we make the edges atoms a little bit closer to increase the interaction.
No, additional interaction. I don't know how to interact. Okay. Maybe some connection with wire or something like this.
Well, we could also.
No, what Vasily, he wants his name written in a ring. You know? Vasily Karchenko, but it will cost.
Next time.
I can say that we've done that. So I didn't show it this morning, but I think we should discuss.
You did? So no, but distribution
of
distribution of Rydberg atoms would be different.
It is different.
Different. And there's even odd alternation. It's a specific of your chain.
So the Rydberg group is a stadium-shaped kind of chain of atoms in which I did see correlations to the J2 function.
No, but of course, once one system is large enough, right, it shouldn't matter.
That's also the hope. Yes.
Yeah, but
Yeah.
when it's large enough in the middle of system, you don't see anything. You remember? It's a flat, yeah.
No, that's not
It's
true.
on average.
No, that's not true.
It's not true.
If you look at a
That's not true. I think.
domain-wide distribution or correlation
I
function.
saw-
You missed the next slide.
Okay, I'll come back to that. Sorry. Getting there. Yeah, so here it seems like nothing happens in the bulk, but it's actually, one nice way to understand this is to look at these single-shot images. So we do have antiferromagnetic chains, but because they kind of occur at positions which can be shifted by 1 or 2 lattice sites, on average, this kind of washes out the histogram here. The order in the histogram is the middle, and of course, because they're always pinned at the edge, it's still visible on the edge. But for example, from the correlation function, you can, for these images, you can convince yourself that there's still something happening in the bulk. So that maybe could be a route to get rid of these edge effects by just looking at a sub-ensemble in the middle of large.
Just to this, I mean, the reason that you see the final correlation rates, so the correlations about long range universes, are, as you said, adjusted the defects. And in 1D, since it's a model which is not number conserving, you would always expect to have some defects in there. One defect is enough to kill. So that's why you get the final correlation. But then if you go to 2D, if you go beyond the correlation threshold, then you can get long range order. But this now depends a little bit on how large your correlation is. Do you know in this adiabatic protocol, is there any knowledge on what the correlation actually is and what determines?
Well, so, I mean, from this we can extract our correlation length to be the order of 5 lattice size.
Well, theoretically, is it long or it depends on?
Well, I mean, theoretically, if you prepare adiabatically your crystal, that should be, that should also be 0, right? This is a perfect crystal.
Well, if you wait for an infinite long time. Right.
Yes. Yeah. So yeah, I don't have a good answer. Here it's just a signature that something is happening.
You cannot wait infinite time because in practice you have some sort of decoherence mechanism.
Yeah.
Which limits.
That's what Kibble-Zurich mechanism presumably describes, right? That's what this Kibble-Zurich is about, right?
Yes.
So I mean, here you don't even have phase transition.
Why not?
Why would you say that?
Even if it's 1D, it's a discrete symmetry, not a continuous one.
Yeah, I know. So it's not. But you always have defects, which the condition to have long-range order is to have 0 defects in one. It's difficult to realize it. Conditions that take into account.
Sure, for any phase transition, the time scale to cross it adiabatically is infinite. I don't know, so in this sense you can never adiabatically reach long range
In
order.
1D, you never have a phase transition exactly. Yeah?
No, you can have a phase transition,
Can
but the time
have,
scale
yes.
is
You can.
Yes, you
anywhere,
can.
ever.
In
Yeah.
1D,
Infinite size limits.
But you have
gastric fluctuation always
there's a
discrete.
decay mechanism, right? So your timescales are limited by.
It's true for everything in the world. I don't know, it's true for any system in solids in your life. No, it's just a question of how many defects you can, you wanna store.
Yeah, first a technical question for exactly that plot of the domain wall. So what you do there is you compare it to the zigzag shape, right? That's why you get also domain walls on the left-hand side, where you don't have any excitation. Or why do you get 4D domain walls at very large negative between? That would be the question.
Yeah, it's because what we define as a domain wall is a kind of, let me show it on this, is this kind of deviation to this antiferromagnetic order.
Yes.
And so initially we start with all atoms in the ground state,
Yeah.
which means one domain wall per atom.
And then
Just a convention.
question related with your superposition in the even chains. Did you try to just switch off the light and hold it and see whether you get some even there? Because if you have the superposition, there could be some dynamics. Or are they general? I think maybe they're general. Looks like it. Yeah.
You can shift them by applying magnetic field
Great.
wave.
So
If you apply magnetic field wave along the line, you can shift the energies.
yeah, interesting thing to try. No, we haven't explored pretty much in detail this. Something we're planning to do.
So what happens if you reverse the tuning ramp to also address adiabaticity, I don't know, for the even or for the where it makes more sense? Have you guys done that? And what happens?
So again, these data are pretty new, so we have tried that initially, but since the time we've tried that, we figured out that there were some kind of technical problem with the way we were doing these sweeps. Like we use the generator with kind of doing steps rather than doing linear sweeps as it should. So we have fixed that, but since then, I don't think we have tried again to sweep back and
No,
forth.
but it does come back.
So it does.
We have some data on that, and we can. I mean, there's
The answer is they
something
do
maybe
come
like
back.
scattering that reduces how much we can bring back to everything in the ground state, but there's no clear structure. There's kind of like delocalized excitations that just might be scattering or something like that.
But
Like
there
what
might be due to
fidelities are we
structures.
talking about? Like each atom's in the ground state like a bit over 80% of the time at the end, in contrast to like 100%. Okay.
Yeah, did you try the time evolution also for the Z3 crystal?
Did you try, sorry?
For the Z3 crystal? So did you try the time evolution crystal?
The quench.
Yeah, the quench.
Yes, we have tried that, and if I remember, I would say the signature is not so clear.
It's not.
Yeah, yes, it's very robust for Z2 order, and less clear for Z3 and Z4. But maybe there's something more complicated.
There's no periodic structure.
It might be too frequent.
It's not a match. Okay. Time for one more question.
And back to Vasily's question, suppose can you try theoretically to take periodic boundary conditions, prepare a perfect crystal, and then let it quench? Would the period still be there?
I think the answer is yes. Hannes, that was for Hannes for sure.
I don't
Yes.
remember.
With periodic boundary conditions, there's oscillation between maybe.
Yeah.
Yes.
Yes, it's
Okay, so with that, I'd like to thank Sylvain again